We have three things I was hoping to talk about today. And so thing number one is a particle selector. It selects particles. You can use it and you can tune it to select particles in a very specific way. I was talking about it at the end of class yesterday. I'd like to reiterate it today. So, a particle selector. Now, these things are all fake. I mean, if you're trying to generate a stream of particles, there's a lot of ways to do it, but getting, and dealing with this, these are contrite little ways in which we can manipulate electric and magnetic fields. So I used the example of it and called it a particle selector on purpose because it does select for certain things, certain attributes. So as we talk about, the usefulness of dealing with the, God, I can't even talk now because I got myself all riled up. The usefulness of steering particles using a magnetic field. One of the things that I want to emphasize is there's a lot of things you can do with this and a lot of ways you can use it diagnostically. A simple idea is what I was trying to mention before, a particle selector. So let me give you an idea of what I'm talking about here. Let's imagine you have a region of space that you could fill with a magnetic field that is into the screen, into the board, like so. And I'm leaving the middle out on purpose because I'm going to draw something in there, but imagine it's uniform within the area of space that's presented. And that you have a stream of particles that are being emitted from this side with some velocity v. Now, there are a lot of reasons why you might want to develop a collimated selected source of particles. And I don't want to go into the full range of it, but just imagine that we have something that is producing this beam of particles. It's not hard to do, and I'll explain a little bit about that process because it comes up on the exam in a minute. But let's assume that we have this, and let's say that for the time being, to make this easier, that they are positive particles. Of course, the first thing I'm going to ask you guys to do is practice the right-hand rule and tell me the direction of the force on these particles as they enter this region of space. You'll indicate it to me by just using your thumb to tell me the direction that the particle is going to be pushed due to its motion through this area. Good. So this particle would experience an upward force as it entered the region of space. And the size of that magnetic force, based on what we've talked about so far, would be QVB sine of 90 degrees as it's passing through that system perpendicular to the magnetic field. Okay? That's the size of the magnetic force on the particle, and it is upwards. All right? Good so far? No big deal? No. You're good? Okay. Now, if we allow the particles to travel in that space, we know from our prior conversation, they will have a circular path until they strike the edges of the container. So if you wanted to, you could steer them back so that they would travel along the length of this column. To do so, you could apply an electric field, because an electric field would provide a complementary force. In fact, we would want a downward electric force. And if done correctly, we might be able to balance the upward magnetic force. Now, it's a positive particle. We're talking about an electric field, therefore, that would have to be this direction, as it would have the effect of pushing the particle downwards, applying a force to that particle, and the electric force would be Q times E. Now, the reason this is important, or the reason why this might be important, is if we want this particle to pass undisturbed through this region of space, meaning undeflected through this region of space, these two forces have to be equal. And if we set these two things equal to each other, then we get something that selects for velocity. And you could tune it so that particles with only a specific velocity would exit the chamber. Now, there's a lot of reasons why you would want to do that. I mean, the most likely is something I already talked about. Old television tubes use a cathode ray tube, and the cathode ray tube would select for velocity. That way you could ensure that your beam of electrons would all be traveling at the same speed, which means they would take the same amount of time to make it to the front of the tube. You could make a device, therefore, that could use the timing of those particles in order to... Someplace. There are lots of places better than here. I think we all want to leave. So, couple of things, though, I want to point out. First, this is pretty straightforward. I don't think this is particularly hard. This idea that you could, bye, have a good day, you could select for velocity, I think is interesting, but point out a couple of other things that you're not selecting for. You're clearly not selecting for mass or charge. Meaning it doesn't matter what the charge of the particle was. You see that too? So whether you sent in a 5 Coulomb charge or an electron, they would experience the same balanced force, balanced set of forces, and would pass through the particle undetected. This only selects for velocity, which means something that was traveling too fast will curve upwards due to the magnetic field. Something traveling too slow would curve downwards due to the electric field. But it doesn't select for anything else. So I'm bringing this up because it also doesn't collimate the beam. If my particles were traveling in this direction, right, it would kind of mess things up a bit. It doesn't collimate the beam. If you're trying to develop a beam of particles that all have the same velocity, this would probably be one of the last steps, not one of the first steps. And this isn't the only way to select for velocity, but this is a way to ensure your particles have a maintained velocity that is, oh my God, you've got it. As a device goes, again, it selects for velocity. It doesn't select for anything else. So if you're trying to make a collimated beam of particles, this is only partially effective. It doesn't tell you that all the particles are going to be the same. In fact, it's not even true that the particles have to be the same charge. They could be positive or negative. It would work the same way. So it selects for velocity only. You saw everything else, of course, canceled out. So in the case of this kind of problem, it has limited use. But for whatever reason, it shows up all the time on the exam. So it's worth pointing out. Now, I want to also indicate they probably wouldn't ask it exactly like this on the test. They probably indicate that you have a set of plates here and might ask what is the potential difference required across those plates in order to cause this to occur. Remember that in situations like this, we're going to start building on principles from first semester. So bless you, the electric field, oh my God, just one is enough. Just get it done with one. You can feel like this vein like throbbing right here. So remember, little stuff like this is going to show up on the exam, and it's going to just be slipped in there. And you might think, oh my God, I have to do all the work to figure out. No, you don't. The potential difference between the two plates is proportional to the electric field. And if you have a set of parallel plates, you can use those things to figure out like what the electric potential would have to be. They'd have to tell you the separation distance between the plates, stuff like that. So just be prepared for stuff that's pretty straightforward like this. And they'll even go further. Which plate would have to be the positive plate? Which plate would have to be the negative plate? This will help you remember how electric fields work. And they work them into these kind of problems in these slow, kind of deliberate ways for you to kind of, like I said, they'll have a problem like this in the test. They don't want to have a separate problem that's all about electric potential. They'll work it in here. And it's a pretty simple way to do so. Now, this also suggests that as the particles exit the chamber, they all have the same velocity. Why would that be useful? There is actually a useful mass spectroscopy or mass spectrometers. They probably don't do it like this anymore. I can't imagine that they would. These are relatively large devices, but a mass spectrometer is going to use a combination of fields to take a group of objects coming through and separate them by mass. So what we just did is separated particles by velocity, but we have not separated them by mass. So if you wanted to figure out how to separate them by mass, you could still use a magnetic field to do so. Imagine that we look at the second stage of what we just saw, another area, a room or something. And I want to draw this, but I'm going to try and draw it quickly because I lost a little bit more time than I planned. My fault. I shouldn't have talked about things that were outside the scope of our curriculum. But imagine I have an area or a room that has basically the exit to the particle we just saw, or the room we just saw. So we have selected for velocity, and now all these particles coming in, we know have the exact same velocity. Once they enter this room, we could separate them by mass. One way to do so would be by using the fact that their mass creates inertia. Now, if you're not following me, well, inertia is a resistance to accelerations. So what I'd like to do is apply a force to this beam of particles that would change the direction of the motion of the particles, but make that change based on their mass. So particles with less mass would probably change more, and particles with more mass would change less. I'm throwing it out there, and I'm saying it like this because I have students who haven't had discussions of inertia in a long time. Remember, inertia is resistance to changes in motion. So if I can apply a force to these particles as they enter the chamber, then I could likely bend some particles more than others. So based on the way I drew this, I'm hoping to bend their direction so that they will curve in a circular path like that. So obviously I'm talking about using a magnetic field to do so. What would the direction of the magnetic field have to be so that positive particles would bend in such a way as to hit the wall in the bottom as directed here? This should be pretty easy based on what you just did a minute ago in your notes. So you're either going to be pointing into the board or out of the board for the ending answer here. Now we want the force on our positive particle to be downwards. The velocity is this way, so you're not selecting for this. You're going to move your thumb into the direction that you want the force to act on the particles. I want the force to be on the particles downwards the moment it enters the area. So, out of the board, I want a magnetic field that switches and is now out of the board, because that will produce a downward force on the particles the moment they enter the chamber. And from our prior discussion, we know that as the particles' velocity bends, it will also therefore change the direction of that force and will always be a circular path. Meaning after a few moments, the particle will be over here, traveling at velocity this way. Do you, in your little notes, need to verify that that's going to change the direction of the force appropriately to produce a circular path? You should check just to make sure. It does. I checked. Now, I want to use Newton's laws here to try and figure out how the mass plays a role in how the particle behaves. This is going to select for mass. So in this case, we're going to use Newton's second law. And I gave you a reminder last class period, yesterday, that I'm expecting you to bring in some of the stuff from your mechanics or AP1 class. In this case, we're going to use centripetal motion. So our unbalanced force will produce a centripetal acceleration on our particles. What's going to cause this force, the unbalanced force, is the magnetic force. So that's going to be QVB, and I'm going to leave off the sign, because no matter how this particle travels in this arc, the angle is always going to be 90 degrees between the velocity and the magnetic field. So it's going to be 1. So I get QVB on the left, and I get mv squared over r on the right. Again, we're trying to select for mass. All right, that's what this does. So now you could select for other things here. You'll notice I can solve for any number of variables here. Do you guys see that? So I could use this system to select for charge if I wanted. Solve this for charge. I could solve for mass. It would select for mass then. It's called a mass spectrometer because one of the things you might notice if we do solve for mass, cancel one of the V's and you'll get QB R over V. Now, don't put a box around that formula. If you want to put a box around anything, put a box around this relationship. But you could solve this for any one of those variables and it would have some usefulness. What this tells me is that, I could pick out where along the wall objects with certain mass will strike that wall. Right? That's what it says specifically. It's based on radius. So some particles that will have one radius, and and some particles have a different radius. The radius and the mass are related. In fact, they're directly related. Objects with more mass will have a bigger radius. So say I want to select for a specific mass, I could actually solve this for R, select for a specific mass, and then just put a hole in the wall at the place where that diameter exists. Those particles would exit with a velocity that, if done correctly, would be perpendicular to the wall because it would have traversed one perfect semicircle. And now you're selecting for both velocity and mass. So this kind of idea, of using this you could also use this as a mass spectrometer, meaning you could send in a sample and you would get a buildup of collisions on the wall. And areas where more mass showed up would show up as being, more collisions. So if you've never heard of a mass spectrometer before, it's a device that gets discussed, I think, most of the time in chemistry. But it's a way of figuring out from a sample all the different masses of the things in your sample. Now, you would have to ionize those things first and then accelerate them to use this as a mass spectrometer. But it's one way of doing mass spectroscopy. I don't know if this is the way it's being done. I doubt it. This seems very idealized. I am sure that chemists have figured out a better way to do mass spectroscopy. But I don't really know for sure. It's not my field of study, and nobody ever builds these. We just talk about them in our classes like this. This is a super, super common problem on the AP exam. This is a good mechanical/electric question that brings in electric fields, magnetic fields, and obviously some stuff from mechanics.
Like, where would the best place to be, like the place to hold? Or
They could ask any number of questions. They could ask, where would you put the hole? They could ask, what would be the mass of particles that would strike this location? Anything like that.
But this format is.
But this is the kind of format. It's all the same thing. It's all set in QVB equals to MV squared over R. So, mass spectroscopy. Now, the truth is, if you wanted to make a collimated set of particles, it would be nice, of course, to probably start with particles that you want to have do what it is that you're going to do. Like, meaning you wouldn't start with a whole bunch of random particles and then try and select for mass, select for charge, select for velocity. It would be better if you could just generate the particles straight away and accelerate them. And so, like in a television, you wouldn't just have some random gas that you would try and accelerate and then select those particles for mass to make sure you were getting electrons. You would just generate electrons. You would have to find a way to do that. There are lots of ways to do that. So, this kind of idealized thing is more an idealized discussion and less this is a real kind of thing discussion. Although this is the way they used to do mass spectroscopy. So, you can see them. There's plenty of pictures of old mass spectrometers, and they all have, some kind of accelerating system that accelerates a gas into this room, and then you have a place where those are going to strike the wall for you to figure out what's in your sample. You should also probably start to realize that you could use this to accelerate particles. That's a little harder to do, but particle acceleration can be done using a similar system. But if you are interested, you should look up cyclotron. It's a device we will talk briefly about. I've worked on a cyclotron before. They don't have to be particularly big. You can have cyclotrons that are small, and they can accelerate particles up to very high speeds. You just need to have a good solid source and a means to cause an oscillating voltage to create a small cyclotron. They can be the size of a disc on a table. Yes, sir?
How do you spell that?
With a C.
Oh, okay.
So it's not an S, it's a C. Cyclotron. Cyclotrons they're in your text.